We're going to go ahead and get started. So we are starting a new unit here. It is not Unit 5. That's mislabeled. But we're starting a new unit, and I think you guys are going to, I don't think this is going to be too bad, this unit. It's writing and balancing equations. The end of the unit can get a little bit tricky, but this one will probably be done with before spring break. And it's basically just how to write chemical equations, how to predict when you look at two reactants what product they are actually going to make. Okay, so this is kind of the stuff like when you think of chemistry, this may be what you think of, is just all the chemical reactions that are happening and how do I know what's going to happen when I mix two things together. Yep.
Just so we're clear, we're having a test before spring break?
Just so we're clear, the plan is we're having a test before spring break. The plan is, yes. Spring break is not for another couple and a half weeks, so we've got time. Okay. Listen up. Have we talked about Ira Remsen and his story about nitric acid and the penny in nitric acid? I feel like, no? No? Yeah, I feel like maybe we talked about it at the beginning of the year. Do you remember that? Like his quote of that stuff? Have we talked about his mutton chops?
No.
I feel like those need to be discussed.
They are disgusting.
They're great. Or disgusting, I guess, depending on your opinion. But
You can pull that off.
I might try that sometime. Yeah, it'll be fun. Okay. So this is a quote by him, and again, I don't remember if I've read this to you before. If I have, I apologize, but it's kind of funny. It basically talks about his first experience with nitric acid, since we're talking about chemical reactions and all of that now. He says, while reading a textbook of chemistry, I came upon the statement, nitric acid acts upon copper. I was getting tired of reading such absurd stuff, and I was determined to see what this meant. This was back in the 1800s, so he writes a little differently here. Or maybe early 1900s, I don't remember. Copper was more or less familiar to me, for copper scents were then in use. I had seen a bottle marked nitric acid on a table in the doctor's office where I was then doing time. I don't know what any of that means. Why was he doing time in a doctor's office? I think that probably means working in a doctor's office. And why did the doctor have nitric acid? I'm not exactly sure, but okay. Anyway, I did not know its peculiarities, but the spirit of adventure was upon me. Having nitric acid and copper, I had only to learn what the words acts upon meant. The statement nitric acid acts upon copper would be something more than mere words. All was still. I don't. Yes, this is a true story. He's recounting his first experience with chemistry, basically. In the interest of knowledge, I was even willing to sacrifice one of the few copper cents that I had in my possession. Whoops. I put one of them on the table, opened the bottle marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. But what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. You guys have actually seen this. We did this at the very beginning of the school year when I put the penny in the nitric acid, and you remember that? Okay? That's what he was seeing. You're just kind of out in the open, and he had no idea this was going to happen. The scent was already changed. Oh, I already read that. A green-blue liquid foamed and fumed over the scent and over the table. The air in the neighborhood of the performance became colored dark red. A great colored cloud arose. This was disagreeable and suffocating. That actually is a poisonous gas that was coming off of this penny at that point. That's why I do it. That's why I do it in the fume hood so that you guys can't breathe that in, right? How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out the window. I learned another fact. Nitric acid not only acts upon copper, but it acts upon fingers. The pain led to another unpremeditated experiment. I drew my fingers across my trousers, and another fact was discovered. Nitric acid acts upon trousers. So now his pants are covered with the acid. Taking everything into consideration, this is the most impressive experiment and relatively probably the most costly experiment I've ever performed. I don't know why costly unless he burned his fingers off, because he just needed to buy a new pair of trousers and get a new penny. But oh well. Yeah, maybe that was a lot more then. It was a revelation to me. It resulted in a desire on my part to learn more about that remarkable kind of action. Plainly, the only way to learn more about it was to see its results, to experiment, to work in a lab. So this guy became a chemist because he burned his fingers with nitric acid. That's not the way I probably would have gone if I'd burned my fingers with nitric acid, but I guess he kind of enjoyed that or something. So anyway, that's what happened with him. I just thought that's an interesting story. Okay, so indications of chemical reaction. We have talked about this already this year. I need to look at these notes. But some things that you can look for to see if a chemical reaction has occurred as opposed to a physical one, right? One of the things is evolution of energy in the form of heat or light. So an example of that is any sort of combustion reaction, right? What do I mean when I say combustion reaction? An explosion, a fire, something like that. Okay, that's giving off heat and light, so that's proof that a chemical reaction is occurring. Anytime you see fire, that's a chemical reaction, right? Production of a gas would be one. So if we make a gas of some sort. Now, you have to be careful with this one, right? If I heat the gas is produced when you combine two room temperature liquids together, and a gas is given off, and it's at room temperature, that's probably evidence that that's a chemical change, because you didn't heat it up in any way, right? Formation of a precipitate. Do you guys remember what a precipitate is? Slash, have we talked about it this year? I don't remember. I feel like we did a long time ago. I can never remember what I talk about in here and what I talk about in AP chemistry. So, precipitate is a solid that falls to the bottom of a solution. You remember that? You mix two solutions. I think the one I did, the demo I did earlier in the year, I mixed two clear liquids together and it turned like this bright yellow solid. Do you guys remember that? Okay, so that's the example of a precipitate forming. Color change, that's actually the one that I did right there. So you pour two clear liquids together and you get a yellow solid. That's unexpected, right? An unexpected color change. So those are the indicators of a chemical reaction, all right, which we've already kind of talked about, but just as a review. This is ammonium dichromate. If we get a chance, maybe later in the year we can do this. We did this at the end of the year last year.
This is on fire.
Yeah.
Other chemistry classes.
Well, no. Ernst did it in the other chemistry class. He was the one who held the fire. He didn't let them hold the fire. So I don't know.
I still want to see it. You can do it.
Well, at the very least, I can probably do it. But anyway, this is just an example of a chemical reaction. You can see a color change there. You can kind of tell that a gas is forming because it starts to just blow out everywhere, right? So there's a couple evidences of your chemical reaction. Characteristics of a chemical reaction, or chemical equation, I think is really what that should say. Okay, the equation has to represent known facts. So now what we're going to talk about is how do we represent chemical reactions? Okay, and we do it with chemical equations. And you guys, I'm sure, have seen equations before, and they probably always look really confusing and weird. I know you've seen equations before. At the very least, you've seen this one. Let's see, which way do I want to go with this? That's not balanced, but what is that? That's photosynthesis. Good. Now, if I wrote it in the opposite direction, it would be... What is it if I write it in the opposite direction? Very good. Cellular respiration. All right. So you've seen, at the very least, that chemical reaction, right? And that's basically just telling you, we're going to talk about sort of what that reaction is telling you, what that equation is telling you, okay? Just a review here, the diatomic elements. We've already talked about this, so I don't know that it might be useful to write down again. If you feel like you've got it, you probably don't need to. But remember our little mnemonic here. I broke clean forks over Nick's head, okay? Because it's diatomic. That's why there are twos, right? Because they come in twos. I broke clean forks over Nick's head. Or you can remember the whole 7 thing, right? Yeah, 7 thing works too. All right, so those are the diatomics. The molecular elements, we did not talk about this. It's probably a good idea to just file this away. Sulfur usually doesn't exist by itself either, but it's not diatomic. It usually likes to hang out in groups of 8. Okay, and then phosphorus likes to hang out in groups of 4. So those are just a couple other things. When you're writing chemical equations, usually sulfur is not just S. It's usually S8. And phosphorus is not usually just P, it's P4.
You ever realize we never use our book?
Yeah. Why don't we use our book? Because I don't really like it that much. Why did I give it to you? So you could have some sort of reference in case you need some extra material to study from. Oh, okay. All right, yeah, I'll let you know. Okay. With chemical reactions, we have to satisfy the law of conservation of mass, okay? Now what that means is, in any chemical reaction, mass doesn't get created or destroyed. Does that seem weird? We don't lose mass, we don't gain mass in any chemical reaction. You know, we may stop a little early today to do a demonstration on that, if I have vinegar, which I'm not sure. Do you have vinegar? Okay. We could do a little baking soda vinegar thing. Have we done baking soda and vinegar yet this year? Okay. Yeah. No, that's the sulfuric acid. Yeah. Wait, did I do that one for you guys? Or did I do that for AP Chem and you just saw the results of it? Yeah, okay. Maybe we can do that one too. Not today, but at some point. All right, so in order to satisfy the law of conservation of mass, we have to balance chemical equations, okay? And so we use coefficients. Now we're going to get to that in a minute, okay? By the way, these aren't my notes. I found them somewhere. So there are people in the corners doing weird things on all of these slides, in case you need a little additional entertainment. I guess they're whispering to each other about the law of conservation of mass. Really an important secret. Okay, this is just another thing on the diatomics, okay? And we've already talked about this, so I don't need to talk about that again. All right, so now we're going to talk about word equations versus formula equations. You're going to have to, we're going to do a lot more with formula equations than we do with word equations, but I want you to be at least familiar with how a word equation works, okay? A word equation, you basically just say everything in words. Surprise, surprise. Here's an example, okay? Methane plus oxygen yields carbon dioxide plus water. Okay, that's the way that you read that. I don't know why I gave you space underneath that, because I don't think there's really anything to do there. Oh, that's what it is. Okay. To label reactants and products. Okay? So then when you're writing a chemical equation, anything on the left side of your arrow is going to be a reactant. Those are things that are reacting with one another. And then the products are going to be on the right side. Those are the things that get produced. Well, you already knew that, didn't you? Kind of? I feel like you should have learned that in biology last year.
Wait, how do you say that methane?
Plus oxygen yields carbon dioxide plus water. Yeah, the arrows usually yields. Which we'll talk about that in just a minute. Okay? And then you've got your formula equation. Oh, there it is. We'll talk about it right now. Yields. Okay, that's what the arrow stands for. All right, so formula equation, you write formulas instead of words, okay? And formula equations, we're going to start with unbalanced formula equations, but we're going to learn how to balance them, okay? So methane plus oxygen yields carbon dioxide plus water. The formula equation for that would be CH4, that's the methane, plus oxygen. Now wait a second. How did I know oxygen is O2? Because it's one of the diatomic elements, right? Okay, so you got to watch out for that. carbon dioxide, we know that one, CO2, and water, hopefully we know that one, right? So that's how you write it as a formula equation instead of a word equation. Guess what one of the things that you get to do is going to be? You get to take word equations and make them into formula equations, right? Which is lots of fun. Okay, this G right here, G, G, and this G down here, which I guess this thing was supposed to be on that line. Those are state of matter symbols, okay? What do you think G stands for? Well, I heard lots of guesses there, but the correct one is gas, okay?
State of matter.
Okay, so here are your states of matter symbols. Solid is just an S in parentheses. This needs to go on your notes, by the way. Liquid is L in parentheses. Gas is G, and aqueous is AQ. Have we talked about aqueous? Well, okay, there is plasma also, but we don't usually deal with chemical reactions in the lab that involve plasma unless you're trying to start a fusion reaction or unless you're standing right next to lightning. Or, I guess, a plasma welder. Well, not supposed to really use plasma or not. Or if they're just called that. But the point is, plasma, we don't have to worry about the, I guess maybe that would be a P in parentheses, but that one just never comes up in here, okay? There's just not a lot on this earth that we experience that involves plasma. AQ, aqueous, means dissolved in water, okay? It's kind of like an additional state of matter, all right? If you've got, and this is normally, not always, but this is normally going to be a solid dissolved in water. And if the solid is dissolved in water, then we call it an aqueous solution, okay? And there's something special that happens when a solid dissolves in water. It usually gets pulled apart, okay? So now you've got ions floating around in water. So we're going to talk about that more when we get to single and double replacement reactions. Okay, so let's skip that part. Some things that you need to label here, okay? Yields is an arrow. Oops. No, don't do that. You see it up here. Yields is an arrow, okay? Reversible is an arrow going in both directions. That means the reaction can happen in both ways at the same time. Precipitate, I did not put on there because you don't really need to know that one. So I only put a few on here, the ones that you need to know. Reactants heated. If you're adding heat to the reaction, there's going to be a triangle over the arrow. Okay, you might see that every once in a while. That one's kind of useful. Or you might see just heat over the arrow. So you see how there's an or there? So you need to put an arrow with the triangle or an arrow with the heat. If there's a catalyst in the reaction, a catalyst speeds up a chemical reaction. Did you guys learn about that in biology last year? Yeah. Talk about catalysts. Okay. So whatever the catalyst is, you can put it over the arrow. So what that's telling me is that the MnO2 is the catalyst in whatever reaction is happening here. Okay. Specific temperature, if it's happening at a specific temperature, then sometimes they'll put that temperature over the arrow so you'll know this reaction is happening at 0 degrees Celsius. Or if there's a specific pressure through atmospheres of pressure. Okay. So that's some of the symbols that you would need to know. I have never seen a down arrow for precipitate in my entire life. I don't think you're going to need to know that one, or the gas, the up arrow for gas. All right. So now we're going to talk about how to balance a chemical equation. What time are we done today? 23. Okay. What time is it right now? 07. Yeah, why don't we stop for now? This is a good stopping point. We'll talk about how to balance the equations tomorrow, and then you'll do some practice on that.